Hello, everybody. My name is Shiva Kintali. I just moved from Princeton 2 years ago, so pretty relatively new to Bay Area. And I was teaching at Princeton University, and most of my courses are related to algorithms, complexity theory, and game theory, and cryptography. And for the last 18 years or so, I've been working in industry, in compiler design, high-performance computing, and artificial intelligence. And now I have a startup. It's called TrueShelf. I'll talk about that in a little while. So the main topic of this talk is I want to give you a high-level overview of blockchain, mostly from mathematical and algorithmic perspective. So we'll be looking at some data structures, what are the mathematical foundations, and how rigorous the foundations of Bitcoin are. So as I said, I was teaching at Princeton, and my course has some of these concepts: hash functions, digital signature, formal verification, zero-knowledge proofs, undecidability, PDAs, and incentive compatibility. And before that, I was a PhD student at Georgia Tech, and again, I was teaching there. And that was almost a decade ago. And for each of these topics, I had to give a different example, different real-world example. But now we are in a world where I can give just one single example for all these concepts, and that is cryptocurrency. So we'll see how all these concepts play a role in designing cryptocurrencies. So let's start with some very basics. For example, cryptographic hash functions. So you all probably heard about regular hash functions, where you have a large set of data, and you want to store that in a small array and use something called a hash table. So the very simple hash function is a modulus function. You take a large number, and you hash it to a smaller number using some modulo, let's say 256 or 2 raised to 256, depending upon the number of entries in the array, right? So here, these cryptographic hash functions require even more important properties. So it's a hash function. Let's represent that as h of x, where x is the input. Input can be any string. That's very important. It can be any document of any size. Digital document, it can be a movie file, a text file, or an image, or any digital file. And the output is always a 256-bit string. And we are assuming that this hash function is efficiently computable. That's essentially, it's linear in the size of the input. So let's say you have a document. It's the size of the document. So the complexity of this hash function is linear in the size of, or at most polynomial in the size of this input. And it must satisfy 3 security properties, and they're very important. That's what distinguishes this hash function from a regular hash function that you are using in hash tables, right? So the first property is called collision freeness. That means if I have 2 different inputs, x and y, and they're not equal, then it's very hard to find x and y that are not equal. X is not equal to y, and they map to the same value. So we are assuming that given any document, it has a unique hash signature. So that's what's meant by collision free. I'll show you an example later, but a quick application of this is in file comparison. For example, if you're using Dropbox, so many people are using file sharing or file storage services like Dropbox, and let's say there is a famous ebook or some movie that you downloaded and you want to store it, then Dropbox, they don't have to store it multiple times. They can simply look at the hash function and make sure that it's the same file and store just one copy of that. So instead of comparing the entire file, you can simply compare the hash functions, which are much smaller size. Right? The second one is called hiding property. So this is where things become slightly tricky. The hiding function is as follows. If you choose a random string, for example, r, and if you concatenate r with x, then it's infeasible to find x if you are given the hash value, h of r concatenated with x. So I'll make it very interactive and ask you some questions and see if you understood things. So why do you think we need this r here? So let's try to understand this statement without r. Let's say I remove the r. Do you think this property breaks? So if I remove r, this property breaks in some situations where the domain is known. For example, let's say I make a list of all the names in this room and say that we want to compute hash functions of all these names. Somebody can figure out hash of my name simply by looking at all the hash functions, by computing all hash functions of all the names, right? So such brute force approaches can be used if I don't use this random string. So that's why adding this random string is often useful to hide the actual content, even when a limited domain.
You can reverse engineer it.
Reverse engineer if the domain is limited.
Yeah.
This is equal to a salt, right?
Sorry?
It's equal to a salt, right? Salt?
It's salt, exactly. This is what's called salt when your passwords are stored in this way. So you add a random salt so that if you have two people with the same password, then you're hiding that information. So one of the important application of this is what's called a commitment. So for example, you want to commit to some particular decision ahead of time, but you don't want to reveal your commitment. So let's say you are trying to vote on some a decision, and you want to reveal your decision. Let's say you want to write a document about what your opinion is about the document, about that decision, and you write the document and compute a hash function and reveal the hash function early on. So everybody reveals the hash function. And let's say after 1 week, people get together and they can reveal their actual documents at that point. And during this 1 week, we know that they haven't altered their decision because the hash function is still the same. We can compute the hash function and see that it's still the same.
I kind of got it, but kind
The commitment?
yeah, the application.
The application, so let's say there are 20 senators that are trying to come up with a decision on some, let's say, global warming, right? They all write their opinion. So instead of telling the opinion, let's say they are revealing their opinion one after the other, then the people who are trying to reveal their opinion later, they can be biased by the people who already revealed their decisions, right? So one way to do that is tell them to write their decisions in a text file and reveal their hash function, the hash value of that file. So they all will write that in a text file. Let's say mine will be shiva.text, and I'll compute the hash of that function and reveal that. And those hash functions will be publicly known to everybody at the same time. They don't have to be at the same time. I can reveal it today, and somebody can reveal it after 1 hour. Because there is no way to compute the actual file from the hash function, you don't know my decision. But I have already committed today. And another important application is patent. For example, let's say you came up with some brilliant idea to improve the Wi-Fi performance, right? So you write a document while your lawyers are waiting to file a provisional patent. You can take a hash function of this and maybe store it on a Bitcoin blockchain. So you can prove that you had this idea 3 months before you actually filed, just in case you want to prove that to somebody. It's a very important use case. We'll come back to more use cases in future. Yeah. So that's property 2. And the property 3 is called puzzle friendliness. Again, we'll see how this is related to Bitcoin. And here, you are given a set of possible values. For example, let's call them y. So you want to compute a hash of x concatenated with r, and you want that to fall into a particular domain, let's say y, right? And actually id. So you want to compute the hash of id concatenated with x, and you want this hash value to be in certain domain. For example, let's say you want the hash function to start with 10 leading zeros, right? So if you want to do that, the only way to do that is by trying all possible values of id. So that's what puzzle friendliness means. So there is no way to, given x and this domain y, the property of the domain y, the only way to compute a valid id such that the hash of id concatenated with x is in this domain y is to try all possible values of id. Okay? So it's called puzzle friendly because there is a puzzle and there is a solver. So it's not solver friendly, it's puzzle friendly. The only way the solver can do it is by trying all possible values. So those are the 3 important properties of cryptographic hash functions. So we're going to assume that all the hash functions that we'll be using in future satisfy these 3 properties. And in particular, we'll be using this hash function. It's called SHA-256, stands for secure hash algorithm, and 256 stands for the length of the output. And I'm not going to go through the details of this. There is a Wikipedia article on this explaining the actual algorithm behind this. There's also a circuit diagram. But this is one of the biggest assumptions, actually. So the assumption is that this hash function is one way. That means given the hash value, there is no way to detect what the actual document is. So that's the assumption that we are relying very heavily on. If somebody finds a way to, and there is no proof that this is one way. That means there is no mathematically rigorous proof that given the hash value, can we compute the actual document. So we are relying on this very heavily, and we'll see where this comes up. But that's an open problem, so if you want to try to solve it. Right? Or even try to find collisions. If you want to find two different documents and which have the same hash function. Nobody is able to find any such collision so far. So that's the basics of cryptographic hash function. So any questions so far? I just want to make sure that, so this is somewhat math heavy, but this is actually undergraduate math. So yeah. So now we are going to the next step. Yeah, sure.
So is this hash SHA-256 common to all blockchain implementations that's happening right now and expected in the future? Or is it just one of the algorithms?
It's one of them, but most widely used. There are some variants of SHA, but this is widely regarded as accepted by crypto community and the NSA, I think.
If somebody's looking into the hardware domain to literally cater to blockchain, then this is an algorithm of high interest.
Exactly. All these ASICs that are developed to mine Bitcoin, they are essentially solving this problem.
In the future, if there's some new algorithm, then it's a different trajectory of developing hardware, implementing that algorithm.
That's right. That's right. The hardware is actually optimized to solve this much faster.
But right now, this is
the one. Okay. So now let's move to the next topic. That's the data structures, where we're going to talk about hash pointers. This is one of the most fundamental concept here. So hash pointer is a tuple. So there are two things. One is the regular pointer, like C pointer, the pointers in C or C++, where you have a pointer to the particular information. And the second one is the actual hash of that information. So hash pointer is nothing but a tuple. The first one is the actual pointer that we all know. Second one is the hash of the data that we are pointing to. So let's remember that. So now we have this hash pointer. We can build several data structures that we already know. For example, one of the most common and simple data structure is linked list. Right? So now we can create a linked list. The only difference is instead of using a regular pointer, we will be using the hash pointer. So for example, here is a linked list where we have a bunch of data, one after the other, and each data has a hash pointer to the previous data. Okay, very straightforward, just like a regular linked list. And one amazing property of this, using hash pointers instead of regular pointers, is we get this new property for free, which is tamper-proof property, right? So let's say we already have this data. We have a linked list of data, and we are every data element has a hash pointer to the previous data. Then let's say I want to corrupt this database. Let's say I want to corrupt the first entry of this data. Then as soon as I change the data, the hash of that data changes, right? But that hash is stored in the next data, next item. So now if I want to genuinely corrupt this entire database, I have to corrupt the next one too. So that means I have to change the hash in the next item. So let's say I somehow managed to do that also. Now the hash of that is already changed in the next item. Now I have to change that, but you have to do that all the way till the end of the linked list. But if you are storing the hash of the last item, let's call it the tail of the linked list, then you can verify that whether it is corrupted or not. So just by storing the hash pointer to the first item of the linked list, you're making sure that the entire linked list is tamper-proof. Is it clear? So that's one of the very fundamental concepts here, and which will be very heavily used in Bitcoin. But try to appreciate this fact. Just by storing the hash of the beginning, we are making the entire one tamper-proof. Yes.
If one of them gets corrupted, then the hash pointer from the previous one will be different.
Right.
And therefore, the linking will break, right? Because no longer can it be able to
It's not consistent anymore. Let's say you want to check the consistency of this linked list. You're looking at the hash of the first one item, and you're making sure that the hash of that is stored in the next item, right? If you change any content here, the hash does not match because of this one-way nature of the...
Or if I have to make it coherent, I have to go and regenerate the hash for the rest of the things.
Rest of the things,
Point
right.
of insertion, something like
Yeah.
that.
Okay, so that's a linked list. So we are implementing a linked list now with hash pointers. What do you think is the natural next data structure to implement using hash pointers? Simple data structure. What comes after linked list in algorithms textbook? Tree, that's right. So let's implement a tree, right? So simple binary tree. So this is called a Merkle tree. It's essentially a binary tree. Instead of using pointers, we'll be using hash pointers. So the figure says everything, right? You have some data, and in addition to the data, you're also, so the leaves are, leaf nodes are where the data is stored. And for every two data items, you store a parent where you're storing both the hash function of the left child and the hash value of the left child and the hash value of the right child. And that goes all the way till the root. Is it clear? So notice that the data is only at the leaves.
How it is organized in memory?
So hash pointers have both pointers and hash functions, right? So you can essentially store it as a regular binary tree. In addition, you'll store the hash value also.
Or otherwise you can have a node which has pointers.
Yeah. That's. I want to make that clear. So I'll not be going through the implementations. I think the next talk maybe they'll be showing some code with some hash values, right? So what do you think are the advantages of using a tree over a linked list? There are obvious advantages from the algorithms world, right? So one of them is proving membership. So if you want to prove that a particular data existed in the Merkle tree, all you need to do is to show the path from the root all the way till the data. So you simply show the hash values on this path from the root to the data, and that proves that a particular data is a member of your Merkle tree. Is it clear? Let's try to appreciate this fact. So essentially, if I give you this path, all you need to do is you compute the hash of the data and make sure that its parent has its hash value as the right child, and that's its parent has the hash value as its right child, and that's its parent has hash value as its left child. So that's all you need to verify to prove the membership. Okay, and the advantage, of course, compared to the linked list is that you will get the membership in logarithmic time. If you have n items as the leaf nodes, so the path that you're providing is only log n length. The height of the binary tree is log n, so that's a proof. It's a proof of membership. So what about non-membership? So let's say I have a set of items that I'm storing in a Merkle tree. So I just showed you how to prove membership. Can we prove non-membership? If you want to implement non-membership, how do you go about it? So one simple idea is look at these data items, simply sort them. So let's say they are some numbers, employee IDs, or any data, right? You can simply sort them lexicographically and show if you want to prove that a particular data is not present in this, simply show two consecutive data elements in this Merkle tree and show that your data that you're trying to prove which is not there, which you're trying to prove that it's not there, is in between these two in the lexicographic order. Okay? So essentially you're showing that a particular data is not in this data, in this tree. So you'll come up with two data elements in this, on these leaves. One is less than this, and other one is greater than this in the lexicographic ordering. So you prove the membership of those two elements. And since you have already sorted it, that proves the non-membership of the third element.
Sorry, question. So when you say sort the hash values?
No, sort the actual data.
Let's say if it's a file, movie file, or how do you
So all these data leaves, they are sorted from left to right. Let's assume that.
And when you say sort of, it could be a file, right? Movie, audio.
It doesn't matter, just lexicographic. They are binary files, right? 0, 1, 0, 1, so on. So just lexicographically sort them.
I see, okay. And so a thing a data which is not a member will probably be on the lower spectrum, lower end or on the higher end, but not in this range.
Yeah, exactly. So you're showing two consecutive elements in the data, and your item that's not present is lexicographically in between these two. But because they're consecutive in the Merkle tree, it doesn't exist.
Yeah, it's not what you said. It doesn't have to be extreme dot correction.
Yeah, so let's say you want to prove the non-membership of 8. You just show that 7 and 9 are in these leaves next to each other.
So the next part is the one that's not obvious, how you prove that.
How do you prove that? You prove the membership of 7 and 9 by showing these paths. And this is a good homework. Given two paths, how do you prove that they are consecutive in a tree?
All the things should match, right? Except they have a common path all the way leading to the leaf node, right?
Yeah. So given two paths in any binary network, how do you prove that they are representing two consecutive leaves? That's a nice puzzle. I don't want to spoil by telling you the solution. Okay, so that's Merkle trees. How about more data structures? So what are the other data structures that we can build using this concept of hash pointers? What do you think? Sorry? Graph. So can we build any graph using this hash pointers?
One way, directed.
Directed acyclic, so that's the point. So we can build any data structure as long as there are no cycles, because there is some dependency in these pointers, right? You are computing the hash of some item and storing the hash of that in the next item. So there is some ordering in this. So if there are cycles, you don't know which item to compute the hash function for. So if you have a directed acyclic graph, then you can start from the sink nodes and compute all the way to the source nodes. Okay. So any non-acyclic structure you can implement using this. So there are actually research projects that are trying to build DAGs. So that's about hash pointers and some data structures. Now we'll quickly look at digital signatures. So this is, I guess, most of you are familiar with this right now. So essentially, we are assuming that there is a function called generate keys that takes key size. For example, let's say 256 is the key size, and it generates a pair. So one of them is a secret key, other one is the address. So we call them as private key and public key. And the private key is what you'll be using when you're spending your Bitcoin. And public key is what you'll give to everybody when they want to send you the money. So public key, as the name states, you're making it public. And we'll also assume that there is a function which is called sign. So any message, if you want to sign any message, you can sign the message using your secret key, and we'll make sure that it's tamper-proof. So let's assume that there are two functions. One is the sign, which takes a message and your secret key and gives a signature that you can give it to anybody. And the second one is verification. So if you signed a document and sent it to somebody, they can look at the message and your signature, and most importantly, the address. That means your public key without looking at your private key. And they can verify that it's validly signed by you. So we're going to assume that these two functions exist. So of course, the requirement here is that all the valid signatures verify. So if somebody validly signed some document using their private key, they always verify. And the adversary cannot forge any signatures. That means if I'm trying to sign something without using my private key, then that's not possible. So the only way to do that is go through all possible private keys. There are 2 raised to 256 possible values, and it's impossible to go through all of them. And in fact, we're going to make this assumption that the hacker is listening to you as you're signing more and more documents. So the hacker is probably listening to you for over a period of time. So he can look at all your Bitcoin transactions in the past and all the documents that you signed in the past. Even then, he's not able to forge your signature. That's the assumption here. Again, I'm not going to the mathematics of those. The main thing I want to point here is that such digital signatures exist, and Bitcoin uses what's called ECDSA, elliptic curve digital signature algorithm. And as I said, the address is your public identity, and the secret is your secret key to sign your documents or to send money to other people.
Yeah, but this is supposed to be proof. What I'm saying is that
With cash,
it's
there
like
could
having
be
a
some
vault.
visual
Like somebody comes
thing
and holds a
also,
gun,
some
open a
video or
vault, I'm going to
whatever.
take all your vault. Right?
No, with cash, there could be some visual thing that got recorded, that's all.
Yeah.
There could be other
Shut down.
witnesses.
Oh, say with the Bitcoin attack, right? So if they do the hammer attack on your Bitcoin,
Well, that's-
it's the exact same thing. It's you now being, something you have is now being stolen.
But what if you're really, really strong and like James Bond and you're not telling any secrets, right? But still people are trying to use hypnotism. So there are conferences at the intersection of hypnotism and blockchain and Bitcoin. So how to hypnotize yourself, hypnotize other people to tell your secrets or passwords, right? So maybe it falls into the domain of this inception, right? Where you're training your brain not to reveal secrets. Or you constantly tell some lie to yourself so that's what you'll reveal if you're accidentally hypnotized. So keep telling yourself some lies, I guess, about the storage of your private key.
Okay.
Yeah, so I just want to make one quick point here is that these addresses, because they are random 256-bit strings, they're not actually telling my name. So as a human beings, like me, like Shiva, or anybody here, are meaningless. All that has meaning here are these 256-bit strings. So that's your identity. Your private key is your public key is your identity. Your private key is your way to spend the money. And so that's why it's called pseudo-anonymous. For example, if I'm making transactions, somebody can follow my transactions and see that I'm probably buying very theoretical books, and maybe I bought TiE ticket and then I went to another conference 2 days ago. They can follow what I bought and infer that it is me, right? So that's why it's not completely anonymous. But there are some implementations of privacy coins that I will not be going through. I think some of the speakers will be talking some implementations of that. So those are the basics that we need. So now let's try to build a ledger, right? Let's try to build a cryptocurrency and try to see how these concepts are used as we are building it. So a simple example is, let's say you have a bunch of roommates and you want to keep track of all your transactions. A simple way to do that is use a ledger, right? You simply add all these transactions one after the other. Alice gets $100, so everybody has $100 in the beginning, and then every transaction you simply add that to the ledger. That's what roommates do. They just keep a book and then add all these logs one after the other, right? So here are some of the problems with this approach, where somebody can be stealing money. Somebody can just say that A paid me $100, and the second one is somebody can just add that I have $200 more. Somebody can be overspending if they have $100, but they are spending $200, and double spending, and maybe they have a secret copy of ledger with all kinds of fake entries, right? So these are some of the problems, and we'll use the technology that we have developed so far to solve all these problems. So the preventing stealing is very, very easy, because every transaction is signed by my private key. So as long as your private key is with you, the stealing is prevented. That's very straightforward, right? Because of the properties of these digital signature algorithms. And the second one is this immutable nature. If you have a ledger that's like a linked list that you're adding one line after the other, if you want to make it immutable, just use the data structure that we talked about before, where you just add these hash values in the every next to the next entries like this, right? So the immutable problem is solved. How about overspending? How do you make sure that people are not spending more than what they have?
You go back and check the transactions to see what they have.
Essentially the same thing. So we keep track of all the transaction IDs a particular person has made in the past. Let's say I have 100 Bitcoins. So make sure that how I'm spending these coins. So there is a way to track all these transactions, but associated with a particular public key, and make sure that the sum is less than what you're trying to spend, or greater than what you're trying to spend. It's as simple as that. You simply keep track of all the transactions. And there is a problem of double spending here. I think by now you heard this multiple times. What if somebody, like for example here, somebody called A, he gave the same Bitcoin to B and A prime, right? So how do you make sure that that doesn't happen? That's again by, so here, so let's say I'm trying to double spend. Try to make sure that you have several confirmations of these blocks. As the blocks are being added into the blockchain, make sure that you wait for at least 3 confirmations. The standard right now is 6 confirmations. Let's say I'm trying to double spend and have 2 different blocks. Eventually, somebody will find that it's an invalid block and stop adding blocks to that particular path, right? So we use this longest chain logic to make sure that there are no double spends. So I will not be going through the consensus algorithm. So I'm skipping lots of steps here, but one can make sure that the consensus and the number of confirmations takes care of this double spending problem. So it's a very simple application where if a university wants to give me a degree, so they'll simply make a transaction from their wallet to my wallet, and every transaction has a data field where you can store any arbitrary data. So they can simply store the hash of my undergraduate degree. I'll show you an example. So that's it. There is a degree that's in the digital format, and they store the hash of that in the transaction. And the transaction is validly signed by Princeton. And we get all the nice properties of the blockchain. Not only that, now I can carry this digital file with me anywhere. So the learners own their digital credentials. And one can do some optimizations using Merkle trees. I'll come back to that later. And we created our own blockchain, again, because of the scalability issues and several other problems. Transaction fees, as I mentioned, and also governance. Bitcoin is trying to become a currency with this off-chain approach. We want a blockchain that is focused on education credentials. And I've already shown this, transaction fees. So the advantages here are that learners control their data. So this is a very important point. Learners controlling their own credentials is very important. For example, my sister was applying for a job back in India, and the employer asked the original certificate. They want to hold the original certificate throughout her tenure, right? So that's not a good idea. They're essentially holding that as a hostage. Same thing happens with passports. Just yesterday, I read some article where some cheerleaders, as soon as they go to some country, they take their passports away. So learners owning their credentials and owning their identity is very important. So very important. And we are planning to expand this to more areas. For example, work experience. One can add work experience on the blockchain, so that you worked at Microsoft from 2011 to 2015, let's say, and real estate records and car titles, right? This is one of the reasons I didn't buy any land in India. They sell the same land to multiple people in India, right? I have no idea to keep track being here. And same thing with car titles, marriage certificates, and proof of existence. In general, we can solve this proof of existence like police reports. I see most of you are Indians here. I was watching an Indian movie recently, and there is some bad guy who bribes the police commissioner and files a police report and bribes him to backdate it, right? So that his report is ahead of the victims. So you can prevent that if you make sure that all the police reports are stored on the blockchain. Their hashes are stored on the blockchain with a timestamp. So you can prevent that corruption. So there is an underlying coin in our blockchain. It's called Euler coin. How many of you know Euler? Have heard of Euler? He's one of the most famous mathematicians. More than 50 mathematical theorems are named after him, so why not a cryptocurrency? That's it. So as I said, all these concepts nicely come together in Bitcoin.
Question?
Yeah. The only thing I haven't touched is the zero-knowledge proofs, but hopefully somebody will cover that.
So all of this focuses on proof of work. Now, there's a concept that was also brought in to make it more green called proof of space, like a storage space. Have you heard? Could you comment on that?
Yeah, there's some startups trying to do that.
Right. So where do you see that based on your?
But storage is also, you're buying some equipment, right? So that's again not environment friendly. If you're buying stacks of memory, that is not recyclable.
But at least there it is purely data at rest, and it more. My understanding was at least that was more direct relationship to the amount of storage space rather than the energy spent. But in computation, currently it's more on the energy spent doing computing. So I thought that. So I was just wanting to see if you had any.
Yeah. So people are coming up with several solutions, but one thing we have to keep in mind is we also have to look at the game theoretic aspects of it. Like how can somebody game the system? Can they announce wrong size of the space and get more power, right? So that's where most, for example, merge mining, that's where it fails. So there are some known, the game theory doesn't work. There are some known attacks that can happen. So I have to look into that, but essentially you need to look at both the incentive compatibility and also the actual working of the system, whether they're contributing proportional to what the storage they have. Yeah.
So on your education thing, unless every university adopts, then it's not working.
Doesn't matter. I mean, we can start with a subset of universities. I mean, we have 50 universities that are using them right now.
And then your same problem, then your fake certificates and hash.
At least we'll start with a subset of real certificates for now, and then let's say we are starting with Ivy League universities in US and IITs in India. So hopefully the other universities will follow. But it depends where the fake certificate market is. Most of them are, so for example, Harvard degree is mostly most in demand. Like for example, in China, there are shops where you can go in and print out and come back, right, with a Harvard degree.
Get a driver license of any state.
Yeah, so it's a good point, but we need a massive adoption, but we need to start from somewhere. Yes.
Could you put the slide up with the two books that you recommend?
So the first book gives you a very nice overview. For example, anybody without any technical knowledge can go through it. Second one is very highly technical. Interestingly, the first book was written like more than 5 years ago, and almost every use case that you hear is already there in that book. It's quite interesting book.
Not just a year ago?
No, this was written 5 years ago. Tapscott was there for quite some time. At least I have the drafts early on. Being at Princeton, maybe they sent it to me, but it was there for quite some time. Okay, if there are any questions.
So given your background in algorithms and all of that, so with whatever has been, what is the challenge right now and expected in the next year in terms of hardware? So let's say somebody is immersed in hardware. So where do you see the current hardware catering to that? Bitcoin, ASICs is one way, but then there is ASIC hardening. But what do you see as the architecture that can, or it's the other way, no matter what architecture, they're going to make it hardened against that, or where do you see that?
Yeah, eventually, for example, Litecoin came up with their own ASIC resistant, they called it, but now it's not ASIC resistant anymore. People have created ASICs that can solve Litecoin puzzle very efficiently. Now there is something called equihash. That's what Bitcoin Gold uses. It's just a matter of time. Maybe in a couple of years, somebody will come up with an ASIC. So there is research from the hardware side, protocol side. It's
groups trying to.
Yeah, it's an arms race from every side, right? But
if you get more powerful, then make it even more hardened, right?
Right.
The algorithm side.
So it's an arms race, and we need to make sure that the incentives are rightly aligned for the greater good of humanity, right? So let's see. I think for the next 10 years, I'm very excited. Let's see how everything evolves. Right now, there is lots of uncertainty and confusions everywhere. Even the governments are confused, right?
So you said every 10 minutes somebody is making 125K, right?
12.5 bitcoins.
So who's paying for all that?
That's a new Bitcoin. It's created out of nowhere. Yeah. Just like the US government does. By the way, US government prints more money than the valuation of Bitcoin every year. If you don't know, that's a fun fact. Thank you.